What happens when we have equal roots? So our determinant, alpha minus 1 squared minus 4 beta, is equal to 0. Then our two roots for the Euler equation are equal to each other. They're both equal to minus alpha minus 1 divided by 2. So obviously, x to the power minus alpha minus 1 divided by 2 is a fundamental solution, is a solution of our ODE. Are we able to find another one? Now we have looked at order reduction, but it's not the approach we're going to be using here. Instead, we want to look a bit, squinting our eyes at the differential operator we have introduced. We want to consider the differential operator, and somehow I wrote it completely wrong. So the differential operator we're considering is the operator that applies to y and gives us x squared y second plus alpha x y prime plus beta y. That is the left-hand side of our ODE. We also want to look at the function that we have used to determine r. That is r minus 1 times r plus alpha r plus beta. Because we have repeated roots, we have that f computed at the root is equal to 0, but also its first derivative at the root is equal to 0 because we have a double root. So it's a parabola that just touches the real axis. Maybe we can extract some of the information by using differentiation on the operator, on the differential operator. Let's look at this. We're computing the differential operator at x to the power r, and we're taking the derivative with respect to r. But the differential operator at x to the power r, we have seen, is actually the same thing as f of r times x to the power r, is the function we use to determine r times x to the power r. So if we're taking the derivative with respect to r of this, where we remember that fr is a parabola with a double root, so it can be written at r minus r1 squared, we have that we're taking the derivative with respect to r of something that we know exactly how to write with respect to r. It's x to the power r times r minus r1 squared. And if we write it down, well, the derivative with respect to r of x to the r is x to the r times logarithm of x. So we have something that has a form r minus r1 squared, x to the r logarithm of x, plus 2 r minus r1 x to the r. But also, we know that the differential operator L is linear with respect to derivatives. So we can take derivatives inside and outside of our differential operator. If we take the derivative with respect to r of the differential operator computed at xr is the same as taking the differential operator computed at derivative with respect to r of x to the r. So it's L computed at x to the r logarithm of x. And the two things we just computed need to be the same thing. So we know that L computed at x to the r logarithm of x must be equal to what we wrote before, that is r minus r1 squared x to the r logarithm of x plus 2 r minus r1 x to the r. But we're setting r equal to r1. So for r equal to r1, the right-hand side that we just wrote is equal to 0 because we have those two terms, r minus r1, in front. So we have that the differential operator computed at x to the power r1 times logarithm of x is equal to 0. But things that satisfied our differential operator applied there equal to 0 are solutions to our initial ODE. So x to the power r1 times logarithm of x is a solution. Let's check the Wronskian to be sure that x to the power r1 and x to the power r1 times logarithm of x constitute a fundamental set of solutions. So we have, on the first line of our Wronskian, the two functions we want to find if they're a fundamental set. On the second line, we have their derivatives. Things cancel out a lot, and we retrieve that the Wronskian of x to the power r1 time and x to the power r1 times logarithm of x becomes x to the power 2r1 minus 1. And that is different than 0. So the two solutions that we have built, x to the power r1, x to the power r1 logarithm of x, constitute a fundamental set. We can also write the general solution as c1 plus c2 logarithm of x, all of it multiplied by x to the r1. Here we actually need x being strictly bigger than 0 because we're taking the logarithm of x. What happens in the third case? So we have seen the case of two real distinct roots. We have seen the case of one unique real root. What happens when we have distinct roots but they're complex? So our delta, that is alpha minus 1 squared minus 4 beta, is negative. Well, then we have that the solution, the r that we're looking at, is lambda plus or minus imaginary numbers times mu, where mu is different than 0. As we did in the case of r not rational, we defined x to the power r as exponential of r times logarithm of x. And this is the definition when r is complex. I would like you to look into that and convince yourself that it still satisfies the derivatives that we are expecting. If we define things like that, then we can write x to the power lambda plus or minus I mu as x to the power lambda multiplied by x to the power plus or minus I mu. Then that is x to the power lambda exponential of plus or minus I mu times logarithm of x. And for the exponential, we have the Euler's formula. That means that you can write all of this as x to the lambda cosine computed at mu logarithm of x plus or minus imaginary part sine mu lambda logarithm of x. We still have an imaginary part. We still have an imaginary number in front of the sine. But we have a theorem that we saw last week or 2 weeks ago that says that if a solution has a real part and an imaginary part, then the real part itself and the complex part are themselves solutions. So they create a fundamental set. So what we have created is that x to the power lambda cosine of mu logarithm of x and x to the power lambda sine mu of logarithm of x are both fundamental sets of solutions. Create a fundamental set of solutions. So I will leave you to check the Wronskian as an exercise to check that it's non-zero. But we have found that the form of the solution of the Euler equation when there are two complex distinct roots is like this. It's x to the power lambda times a coefficient cosine of mu logarithm of x plus a coefficient sine of mu logarithm of x.